Oh right, so today we're going to tackle January, well it's February 2012, Equilibria, energetics and elements. So, first of all, we're going to kick off with a rates question. It gives me a rate concentration graph, notice rate concentration, and then it gives me some initial rate experiments, and I need to determine the order with respect to iodine, propanone and hydrochloric acid. Okay, so first of all, let's do iodine. Hopefully you can see, what I'll do is I will write it up. You can see that the rate does not change as you change the concentration of iodine, and therefore, so as it increases, and therefore it is zero order with respect to iodine. Oh right, so for the next one, let's use the initial rate experiment. So, experiments 1 and 2, you can see that the concentration of propanone has doubled, as has the initial rate, and therefore we can say from 1 and 2, if the concentration of propanone times by 2, the rate times by 2, and therefore it's first order. With respect to propanone. For the next one, so let's do HCl. That stays the same if we use 2 and 3. That, if you actually times by 2.5, that you also times by 2.5, and therefore, so we can say from if we do concentration of HCl is times by 2.5, the rate is times by 2.5, and therefore it is first order with respect to HCl as well. Okay, so I can now do my rate equation. So the rate is equal to my rate constant times the concentration of propanone and the concentration of HCl. Iodine I don't need to put in it because it's zero order. It wants me to work out the rate constant. So the rate constant is going to be the rate divided by the concentration of propanone times the concentration of HCl, which, let's use experiment 1. That's going to be 2.10 times 10 to the minus 9 divided by, if I just go along here, 1.5 times 10 to the minus 3 times 2.00 times 10 to the minus 2. If you put that, what I would do is I would work that one out first and then divide that by that, just to make sure you actually get it to be 7.0 times 10 to the minus 5. 4 units, rate is in moles per decimeter cubed per second. These guys here are both in moles per decimeter cubed, so that's moles per decimeter cubed squared. One of those will cancel out with that, so the unit will actually be moles to the minus 1, decimeters cubed, seconds to the minus 1, because you're going to put those up top. Oh, right, so now I need to get, now I need to work out a possible two-step mechanism. The key thing to do is in your rate determining step, you must have the species that are in the rate equation, which are those two. I've got to make one of these products, so let's see what will go. Well, if my H maybe goes off with my I to give me HI, and then I could have HCl as well, which is one of my products. Now, HI isn't actually one of my products over there, so if I now use that HI and I react it with this other ICl, that could give me iodine, which is one of my products, and another HCl, which gives me my two HCl as my products. Okay, the next thing is it wants me to confirm lattice entropy is formation of 1 mole of an ionic compound from its gaseous ions under standard conditions. So that's relatively straightforward. Not bad for 2 marks. It then wants me to complete by using the letters that it gave me on the previous page. Here we go. These are the letters that I need. This one is going to be the formation of sodium oxide. This one is going to be the atomization of sodium, which is E. This one here is going to be the atomization of oxygen, which is D. That's the first ionization energy of sodium, C. This is going to be the first electron affinity of oxygen, A. Second electron affinity of oxygen is B. And of course that is my lattice entropy there. What I'm also going to do is we're going to calculate the lattice entropy. So I'm going to put the numbers on. Remember, this is 2 sodiums, so it's going to be 2 times 108, which is 216 for the ionization. This is for the atomization of sodium. That's 249. That is actually 2 times 496, which gives me 992. A for the electron affinity is minus 141. This is 790 for the second electron affinity. That's what they want me to work out, and that is minus 414. So if you do that, you should get delta H lattice is equal to that number minus everything else in the brackets. So it's going to be, if I go around, 790, 141 plus 992 plus 249 plus 216. Going all the way around, that equals minus 414 minus 2,106, and if you do that, you should get 2,520 kilojoules per mole. Right, okay, so why is it difficult to predict whether the lattice entropy of magnesium sulfide will be more or less exothermic than sodium oxide? Well, okay, let's compare the cations first of all. The magnesium cation is the smaller cation and has the higher positive charge. Therefore, it has the higher charge density and stronger attractions. And we can also say for oxygen, although it has the same charge as, sorry, oxide has the same charge as sulfide, it's the smaller anion, and therefore again it has the higher negative charge density, and therefore forms the stronger attractions. So you don't know which one's going to be more important, because magnesium is a stronger cation in terms of forming ionic bonds, sodium is a stronger ion in terms of forming ionic bonds. If you put those together, it would be happy days. However, they are bonded to the 2 of the weaker ones, so you don't know which ones are most important. Student wants to determine the lattice entropy of sodium carbonate. Very difficult to do using a similar Born-Haber cycle. Why? It's because you need the formation of the carbonate anion as well, which you don't have. Student thought you could determine the lattice entropy of sodium carbonate using entropy change solution, which is exothermic. Okay, that's really important. Sketch this Born-Haber cycle. Okay, so you start, I generally start at the top. So at the top you've got 2Na plus gas plus CO3, 2 minus in the gas. That there is going to be your lattice entropy of sodium carbonate. So down here I put Na2CO3 solid. Then, because they told me it's exothermic, going down again is going to be Na plus to aqueous plus CO3 to minus aqueous. That is delta H solution of Na2CO3. And then down this side, you're going to have two steps. The first step will be 2 times delta H hydration of Na plus gas. And then this one will be delta H hydration of the carbonate ion gas. And that gives you, so delta H lattice is going to equal 2 times delta H hydration for Na plus gas plus delta H hydration for the carbonate ion. And it's also going to be minus delta H solution of sodium carbonate solid, like so. Because that side has to equal that side.